Welcome class to the lecture video on section 5.7. This lecture video will cover the 100 times 1 minus alpha % confidence intervals for the mean of pair differences, which we represent with mu subscript d, or as you'll hear me just call it mu d. So in real-world research, we often concern ourselves with comparisons between two populations. For some research, it might make sense to pair our data values. We can then make estimates and draw inferences about the differences between the pairs. So what this looks like is we may have two separate populations of equal sample size, and we compare ourselves with their differences. So, and by differences, we do mean to subtract. And so we would have x1 minus y1, x2 minus y2, which would form our new set of data of d1, d2, all the way to dn. So an example of when this situation might arise is if you suppose you run cross country and your coach may, or probably would, measure the amount of time it takes you to run on your first day of practice and then how fast it takes you to run on your last day of practice. And your coach would not only do this for you, but all the other people who are running cross country. This would be an example of something we would want to pair because we'd be curious to see the differences in how fast you ran on your first day and your last day. And similarly, we would want to see how fast, say, Johnny and Susie were running on their first day and last day. What we would not want to do in this situation would be compare how fast you could run on your first day of practice and how fast Susie ran on her last day of practice. That wouldn't make sense. So we have this thing called natural pairing, which occurs when comparing different things to each other wouldn't make sense. As in, it wouldn't make sense to compare your first day of practice to Susie's last day of practice, or Johnny's first day of practice to your last day of practice. That doesn't make sense. We wouldn't do that. We would compare your first day and last day. Now, sometimes that before-after pair differences occurs when we have this before and after research. Now, that's not always the case. Sometimes the pair differences arise in other ways. For example, if we think of a hospital, we may be concerned about the number of patients we see in the ER and OR, and we may compare this over different hospitals. So hospitals, say 1, 2, 3, and so on. And so it would make sense to compare the number of patients to ER and OR to pair by their hospital. It wouldn't necessarily make sense to compare the number of patients in the ER at hospital 1 and the number of patients in the OR in hospital 3. So we still have that natural pairing, but it's not necessarily before and after. But that before and after situation is definitely the most common scenario that we see. So if we're going to be constructing a 100 times 1 minus alpha % confidence interval for the mean of pair differences, we're going to use the formula of d bar plus or minus t n minus 1 for comma alpha over 2 times the standard deviation of d over the square root of n. And this d bar, that is the average of our differences. So if we scroll back up, our d bar comes from adding up our d1 plus d2 plus ... all the way to dn and dividing by n. And then we will use the t distribution, which you should be familiar with, and SD, we're going to use a formula very similar to what you've already seen for calculating standard deviation, only instead of x, we're going to be using our d values. So you basically actually treat a paired sample the same as you would a one sample. It's just you have to do that first initial step of subtracting your data values. Once you've done the subtraction, This is your one sample, and your formulas are very similar from there. So for our standard deviation of our differences, that would be equivalent to the square root of the summation of d squared minus the summation of d squared divided by n, all divided by n minus 1. Or you could also similarly use the square root of the summation of d minus d bar all squared divided by n minus 1. So to take a look at an example of this, let's say we have subjects that are at the beginning at the beginning of the program, and we are looking at before the program begins and after the program begins. Wow, that did not come out clearly, did it? All right, so we're going to be looking at serum cholesterol levels for 12 subjects before and after diet exercise program. So we've got our before data that we'll call our X data and our after data that we will label Y. And we are being told that our difference is after minus before. At this point, I should tell you to be very careful when you're reading these word problems. Make sure it's clear whether it's after minus before or before minus after. A lot of times it is after minus before, but read carefully, make sure that it's very clear. In the event that you're reading the problem and it isn't clear, you can choose, but just make sure you choose consistently. And what I mean by that is if you decide to do after minus before in your calculations, when you provide that interpretation of your confidence interval, make sure that you're still talking as if it was after minus before difference and not before minus after, because that would be that either your calculations are incorrect or your interpretation is incorrect. Either way, you'd lose points. So applying this example problem, we would first need to collect our D bar. So by adding up our D's and dividing by our sample size of 12, we will get a mean of negative 20.17. Using our formula for sample standard deviation, we'll take the square root of the summation of d squared minus the summation of d all squared divided by n, all divided by n minus 2. Plugging in those values, we would get a standard deviation of the differences to be 23.131. All right, so still moving on, as we need for our confidence interval, we need to calculate our t-value. So if we think about this in terms of steps, finding our mean was step 1, finding our standard deviation was step 2, step 3 is calculating our t-value or using the table. So we are asked to construct a 95% confidence interval. So in order to calculate alpha over 2, that's 1 minus 0.95 divided by 2, which equals 0.025. And for our t-value, we have our degrees of freedom of n minus 1, which equals 12 minus 1, which equals 11. So our t-value will be degrees of freedom 11 with alpha over 2 value 0.025, which if we use our table, gives us a critical value of 2.201. And again, you can find this on table 4, or if you're looking at the back of the book, I have it as table, I believe it's A3. And from here, we have all the pieces we need. We just have to plug into our formula. So plugging in our average of negative 20.17 plus or minus our critical value of 2.201, our calculated standard deviation divided by the square root of our sample size. From here, we can simplify to have negative 20.17 plus or minus 14.70. And this means that our 95% confidence interval, the mean difference is from negative 34.87 to negative 5.47. Now, thing to notice, so this confidence interval was strictly negative. And when we are doing this, that means we're subtracting y minus x, our after minus before. Now, because our values were strictly negative, our confidence interval, that implies that our before data was larger than our after data. What does that mean? Well, that means that our cholesterol in the before was larger than our cholesterol after. For us, that would have probably been the goal with diet and exercise program. Our goal was to see a lowering of that cholesterol, and because of our negative confidence interval, that means we succeeded in our goal. That's a good thing. Now, I'll leave it to you to do the interpretation on your own, but it should go something along the lines of, we are 95% confident that da 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 da. Now, in order to use this formula and to do your confidence intervals for paired differences, we need to have the following assumptions, and that is that the differences are approximately normally distributed and the differences are independent of one another. And what I mean by independent of one another, obviously with paired data, our before and after aren't going to be independent of each other. What we're talking about is, speaking of our hospital example, hospital 1 is independent of hospital 2, which is independent of hospital 3, and so on. For the example we just did, each of these subjects are independent of each other. That's what we mean when we're saying that they are independent. One special note about this, if our sample size is greater than or equal to 30, then the values of our t-distributions are almost identical to the corresponding z-values, which I have mentioned in the past that once we get to 30, t essentially becomes z. So when our sample size is greater than 30, that means we can construct our confidence interval using our z alpha over 2 in lieu of our t critical value. Some professors have strong feelings about this, depending if you guys were taking, say, 211 instead of 215. I know certain professors who teach that class would tell you that no, regardless, always use the t-value. Some have this, okay, as soon as you hit 30, since it's essentially z, you should use z. In order to keep it consistent with the notes and what has gone on in the other lecture videos, I'm going to tell you to do the second method. So if your sample size is less than 30, use your t-distributions in your t-table. Once that sample size hits 30 and above, go ahead and use the z-table. Okay, so that brings us to the end of section 5.7 lecture video and the last section of this week. Please make sure to do your homework and complete your quiz on time. Have a good night, everybody.